So what are these intermolecular forces? The strength of them depends on the structure of the particles, and the state of the matter at a given temperature depends on the strength of those intermolecular forces. When we have strong forces, we're going to have high melting and boiling points. Weak forces will give us low melting and boiling points. These intermolecular forces arise from interaction between charged particles. We've got we can have actual ion charges, we can have partial charges, as in a polar molecule, or we can have temporary charges on particles. But they are an attraction between electrical charges. So Coulomb's law is useful here as well. This part is a constant, and we don't really need that part. E is proportional to Q1, Q2 over R, and we've looked at that before. The potential energy E of two oppositely charged particles, and the charges are Q1 and Q2, decreases. It becomes more negative. They become more attracted with higher charges and with decreasing separation. This is the separation between the particles. So stronger charges, smaller distance, will give us a more negative potential energy. And again, negative potential energy is good. Things are going to go to the lowest potential energy. So when things are close together, we get the best attraction, and when the charge magnitudes are larger, we get the best attraction. Bonding forces are different than intermolecular forces. Bonding occurs within a molecule. Here we have an illustration of a water molecule, and there's a covalent bond between the oxygen and the hydrogen. And the distance here is very small, 96 picometers. And in a sample of water, the distance between one molecule and the next is about 3 times that, 300 picometers. So they're still relatively close, but they're not nearly as close as the oxygen is to a hydrogen within the molecule. So distances are larger, and so the intermolecular forces are much weaker. So now we're going to talk about the individual types of forces. We'll talk about 4 different forces. The first one is a dispersion force. This also has a lot of other names. Van der Waals forces, London dispersion forces, induced dipole forces, all sorts of different names. I'm going to try to stick to the book's term, which is a dispersion force. The dispersion force is present in all molecules and atoms. Everything has dispersion forces. So let's look at where this comes from. So if we look at an atom, and this would be helium, because there's 2 electrons and there's 2 protons in there. If we were to look at helium's electrons at any given time, we would see on average that they're probably spaced out within that 1s orbital, but we could catch them both on one side of the nucleus, as we do in frame 3. Because again, electrons are particles and they're waves, and so you can't predict where they're going, how fast they're going. We can take a snapshot of them and pinpoint them. Oh, it's there, but then we don't know anything about its movement. So here we're just taking snapshots, and we've caught the 2 electrons over on this side. This reminds me of a time I came into the living room, and all 6 of my children were piled on half of the couch. Very, very random thing. I think they were looking at something on somebody's phone, but that just doesn't happen, right? Usually they're scattered about. Even when they all lived at home, they were never all on the couch together. But it can happen just randomly that these 2 electrons will be on the same side of the atom. When that happens, these are the negative charges, and the nucleus is the positive charge. If all the electrons are on this side, then this side of the atom becomes slightly negative, and the other side becomes slightly positive. Does that make sense? Another analogy is a boat. You go to San Francisco and take one of those cruises that goes out in the bay and go around Alcatraz, right? And you get people. People are the electrons on this, in this analogy. So if this is the boat, the people are out on the deck and they're milling about, and you could have the people all rush to one side, right? Could be spontaneous. It could be that they're attracted to something, like you're going around Alcatraz, and so they all go to that side so they can see better. Could that make the boat list a little bit? Yeah, it could. It's probably not going to be significant, or they wouldn't let that boat out with all those people on it. But it could cause the boat to tip just a smidge, right? So that's what's going on here, is the electrons just happen to be unequally distributed, and we get a small separation of charge. That's called an instantaneous dipole or a temporary dipole. It doesn't stay that way. It goes back, and then an instantaneous dipole can happen again. And these things come and go very quickly. But when we have an instantaneous dipole in one atom, it can induce an instantaneous dipole in a neighboring atom. So here we've got one that's lopsided. This one started it all, and so its electrons just happen to be over here, and so this end of the atom is a little bit positive. Well, the neighboring atom sees this partial positive charge, and that attracts the electrons. It's like going around Alcatraz, and the people are attracted to that. They're wanting to see what's happening. So the electrons are attracted, and that causes a dipole in this atom. And this one now is going to cause a dipole in a neighboring atom, because this one's lopsided, and so it's going to pull the electrons from another one. Does that make sense? This attraction between the instantaneous dipoles is what's known as the dispersion force. It occurs in all atoms, all molecules. Everything has dispersion forces because the electrons can get lopsided. It's not a very strong force. It's a weak force. It's very weak, but it's there. And these instantaneous dipoles, although they are extremely brief, they also happen a lot. And so a lot of little things adds up. You heard the expression being pecked to death by a duck? Well, it's a good one. Think about a fly. Maybe you're trying to do your homework and this fly keeps landing on your nose and your head and your arm. And is it hurting you? No. But it's annoying, right? And it keeps doing that. And after it's landed on your hand for like 1,000 times, you're ready to nuke the house to kill this fly, right? It's just so annoying. It's a lot of little tiny things. It just builds up. And that's what the dispersion force does. And it can become quite significant. So the magnitude, how big this force is, depends on how easy it is to shift the electrons around. How easy the atom can be polarized to form an instantaneous dipole. So if we have a larger electron cloud, the electrons are held less tightly. They're further from the nucleus, and they're easier to push around. I think of like xenon here as being just a big flabby molecule, and you can just push its electrons around. A small molecule like helium, we've got 2 electrons in there, and they're much closer to the nucleus, and they're going to stay closer to the nucleus, and they're going to be harder to shove around. So a large molecule, a large atom is more polarizable because the electrons can be pushed around more easily. So we see that the dispersion force increases with molar mass. So here are the noble gases. Here's their molar mass, of course, getting larger and larger as we go down the group 8A in the periodic table. And here are the boiling points in Kelvin. And looking at the boiling point gives us an idea about the strength of the intermolecular forces, because helium only needs a temperature of 4.2 Kelvin, which is very, very close to absolute zero, in order for those particles to get away from each other. The dispersion force causes the atoms to be attracted to each other, to sort of stick together. I think of it as being a bit like Velcro, kind of stick together. But with helium, that Velcro is very, very weak, and so it takes very little kinetic energy to cause it to move away. As we go down this group, we see that the boiling point increases, and for xenon, it's 165 Kelvin. This boiling point is much higher than for helium. And the only difference here is that xenon is a larger atom, and its electrons are easier to polarize, and so those induced dipoles, those dispersion forces, happen more, and they're more significant. Any questions? The shape of molecules also plays a part. Here we're looking at pentane and neopentane, and these, here are their Lewis type structures. These are both have the same number of carbon and hydrogen atoms, so they have the same molar mass. They're the same size, right? But their shape is different, and their boiling points are going to be different. So molar mass is exactly the same. This one boils at 36 degrees Celsius. This one boils at 9 degrees Celsius. And the difference is the shape. For N-pentane, the carbons are in a relatively straight chain, and so the molecule has sort of a capsule shape. There is a larger surface area here on the side for these two molecules to be attracted to each other. In neopentane, there's a central carbon with 4 carbons around it, and that gives us a more spherical molecule. And so when these molecules try to get together and be attracted by dispersion forces, there's just a small point at which they can get close enough together. So if we're looking at similar elements or compounds, molar mass is useful. But there are other things like shape that also play into this. This example is where I think the Velcro makes a lot more sense. If you think of this as being covered in Velcro and that one being covered in Velcro, right? These two are going to stick together much stronger than two spheres that can only hit at a little tiny point, right? You've seen those bounce house things where you put on a Velcro suit and you jump against the wall and your body sticks, right? It holds your whole body off the ground. And yet you've got this shoe with a Velcro strap that will not stay stuck, right? Because it's a little tiny area of Velcro, right? Compared to the area of your body hitting the wall. Any questions? Here's a graph showing the boiling point of some substances as a function of molar mass. Here we're looking at straight chain alkanes. So these are all long, skinny molecules. We're not having any that are spherical, so that we're not altering the shape. We're just changing the size, the mass. And we see that as the mass of the molecule increases, its boiling point increases as well. These sorts of comparisons are the sort of thing that are important in organic chemistry. Being able to look at what does the molecule look like, what are the types of intermolecular forces, and being able to predict relative boiling points. So which halogen has the highest boiling point? Cl2, Br2, or I2? I2, right? And why is that? It's the largest, right? Bless you. So chlorine would be about 70, and Br2 would be about close to 160. And iodine would be, about 250 grams per mole. Larger atoms, larger molecule, electron cloud gets big and floppy, basically, and you can push it around. And so these dispersion forces become more significant. Second force is called the dipole-dipole force, and this is found in polar molecules. Dispersion forces are found in everything. Dipole-dipole forces exist in all molecules that are polar. They're stronger than dispersion forces because these are attractions between permanent dipoles rather than temporary dipoles. So if we look at these molecules here, two molecules of the same compound, and they are polar. The molecule is polar. This end is also always a little bit negative. That end is always a little bit positive. And so we can have a constant attraction between the negative end of one and the positive end of another molecule. And here we're looking at the electrostatic potential map. We see there's more electron density here and less here. And so the opposite ends are attracted a lot like magnets. So polar molecules have the dipole-dipole forces on top of dispersion forces. So we find that polar molecules have higher melting and boiling points than nonpolar molecules of a similar size. So here we've got formaldehyde and ethane. Molar masses are extremely similar. Here are their Lewis structure type, as structural formulas. And here we see on this carbon, we have no lone pairs, but one of these atoms is an oxygen and the other two are hydrogens. This is not symmetrical. And so this is a polar molecule. Here, the carbon is surrounded by hydrogens and another carbon. Carbon-hydrogen bonds, remember, are nonpolar bonds. And so this has no chance of being polar. The boiling point here, minus 19. Boiling point here, minus 88. And again, a difference in the melting points. The nonpolar molecule melts and boils at a much lower temperature than the polar molecule. Here we have another graph showing boiling point. This time it's as a function of dipole moment. So this would be the magnitude of the dipoles on these molecules. And they've chosen molecules here that are very similar in size, so the dispersion forces shouldn't be a factor here. But we see that the boiling point increases as the dipole moment increases. The more polar the molecule is, the stronger the force of attraction between the molecules is. Polarity of molecules is very important in discerning or determining miscibility. So this is it's a weird word. Mixability, not actually a word, but you probably know what I mean by that, right? Are they mixable? Can you mix them together? That's what miscible means. Two liquids are miscible if they will mix together without separating. So here we have an illustration of, looks like pentane and water. And the pentane is all carbon-hydrogen bonds. They're all nonpolar bonds. This is a nonpolar molecule. And here we have water molecules, and the water molecules are polar. So these are attracted by dipole-dipole forces that are much stronger than the forces that are attracting the pentane molecules to each other, which are just dispersion forces. And so the water molecules are attracted to each other very strongly, and they won't let the pentane get in. They push it out. And sort of a little saying that we use to predict miscibility is like dissolves like. That means if you have two polar compounds, they'll probably mix. If you have two nonpolar compounds, they will probably mix because they are alike. But one of each, probably not. Again, general rule of thumb, lots of exceptions. So, which of these molecules have dipole-dipole forces? Well, first of all, what kind of molecules have dipole-dipole forces? Polar molecules. So we're looking for polar molecules. And here my two criteria method, instead of drawing stuff and thinking about vectors, works really well. Are there any lone pairs in the central atom? Are all the atoms bonded to the central atom the same, or do they have the same electronegativity? If there are no lone pairs and all the atoms are the same, it's nonpolar. If you have a lone pair or a different atom in there, it's going to be polar. So we may need to look at a Lewis structure. This is Ci4, and I wrote out the name here because it can be confused with Cl4, which is not a thing, but students don't always recognize that. So Ci4, there'd be 4 iodines around that. And, we should count out all the electrons and stick them around and everything. Because if there was a lone pair in the central atom, that would affect its polarity. Could there possibly be a lone pair on the carbon there? No. Because carbon is in the second period, it can only have an octet. It's not possible to expand its octet. So here we have 4 things bonded to it. We know that carbon likes 4 bonds. And so that's what the bonding structure is going to look like. On this central atom, no lone pairs. All the atoms bonded to it are the same. Is this polar? It's not polar, right? Because the 2 things are correct. So this is a nonpolar molecule. Does it have dipole-dipole forces? No. CH3Cl. Well, again, carbon in the middle, and there's a Cl, and there's 3 hydrogens. And again, the ideal thing would be to figure out how many valence electrons and everything. But again, with the carbon, it cannot expand its octet. So we apply the rules again. Are there any lone pairs on that central atom? No. But do all of these atoms have the same electronegativity? No. Hydrogen and chlorine are different. What that means is that this is not symmetrical in terms of its attraction for electrons. It's going to make a tetrahedral shape, but one of those is more electronegative, and it's going to pull electron density away. So this molecule is polar. Why did I start writing that? I don't know. Will that have dipole-dipole forces? Yes. Yes, it will. Then the last one, HCl. How do we tell if that one's polar or nonpolar? Well, there's only one bond, right? So is the bond polar? Yes, it is. And all I expect you to do there is look at these and say, are those 2 different nonmetals? Yeah, they're different. That's probably polar. That's what I would expect you to say. So that can also have dipole-dipole forces. If we looked at something like chlorine, Cl2, there's one bond here. If the bond's nonpolar, the molecule's nonpolar. These are 2 atoms of the same element, same electronegativity, right? So that's going to be nonpolar. Any questions? Here we have an electrostatic potential map for acetonitrile. Oh, yeah, it's a formatting issue. Ignore that. So this is the electrostatic potential map. And we see that there's red here and there's sort of a darkish color over here. That's indicating that there's more electron density at this end than at that end. And it's saying from this map, determine the geometry for how two acetonitrile molecules would interact with each other. Which of the orientations shown to the right is most likely? So from this map here, we can identify that this is the partial negative end, and this is the partial positive end of the molecule. So then if we look over here, this is the nitrogen, and that's the carbon end. So nitrogen, and this is the carbon-hydrogen end. Where would the dipoles be on there? We'd have a partial negative here and a partial positive there. This is partial positive, this is partial negative. Would there be attraction between these two? Yeah, there would be. What about here? Again, we'll label these. They're positive and negative ends. Is there going to be attraction the way these two molecules are lined up? No, because the two negative ends are close together. They're going to repel each other. So that's not going to work out. How about this one? Is there going to be much attraction there? Not a lot. There might be some attraction here, but they're much farther apart, the charges are. Here, they were as close as they can get. And then down here, so this isn't going to work. And then for D, we have the two negative ends next to each other. Is that going to work out very well? No. So it must be A. What they're asking here is basically, so I've got a north pole and a south pole of a magnet. And I could have a couple of different orientations. Which one is going to stick together the best? The one where I have the two north poles next to each other, the north and the south pole close to each other, or here nothing's really close to anything. All right, we're going to get better attraction here because the opposite poles are next to each other. Does that make sense? And so that's what's going to happen with these molecules. The molecules act like little bar magnets, except instead of magnetic charges, it's dealing with electric charges. Third type of intermolecular force is called hydrogen bonding. And the name here can be misleading. Hydrogen bonding is basically super dipole-dipole force. Okay? It is the same type of attraction as dipole-dipole force, the attraction between two molecules that are polar, but it's just extra strong. So this is found in molecules that have hydrogen that are bonded to fluorine, oxygen, or nitrogen. And that makes the polarity of this molecule extra big because nitrogen, oxygen, and fluorine are the most electronegative elements, and they're very small, so that the neighboring atoms can get closer to each other. So the dipole moment of the molecule is larger, and the molecules are able to get close to each other. So we need to be able to predict which molecules will have hydrogen bonding. And the key here is fluorine, oxygen, or nitrogen bonded to hydrogen. You familiar with the movie E.T.? What did E.T. want to do? Phone home, right? Phone home. E.T. phone home. Can you remember that? So we're looking for fluorine, oxygen, or nitrogen, phone, connected to a hydrogen. And if you've got that, you'll have hydrogen bonding in your molecule. The hydrogen bonding is dipole-dipole force, but it's extra strong. And it's such a significant difference that it actually has its own name. Let's look at this one. Here we got hydrogen bonding in water. So in the water molecule, do we have fluorine, oxygen, or nitrogen bonded directly to hydrogen? We do. We have this bond. So we are going to have hydrogen bonding. This bond here of the hydrogen to the oxygen is not the hydrogen bond. That is a covalent bond between hydrogen and oxygen, but that's not what a hydrogen bond is. It's kind of confusing. The hydrogen bond is the electrostatic attraction between neighboring molecules. Okay? It's an intermolecular force. This is an intramolecular force called a covalent bond. So it's between one molecule and the next. And so that fluorine, oxygen, or nitrogen will be the negative end, and the hydrogens will be the positive end, and then they'll be attracted to each other. And this attraction will be greater because the magnets are stronger, essentially. If you've got two little bar magnets, and they'll stick together, and then if you have like two of those neodymium magnets, the really strong ones, or ceramic magnets, and they go clunk, and they clunk together, and they're much harder to pull apart. Why? Because they're stronger magnets, right? So these molecules are like stronger magnets. The force of attraction is much larger. So here in the shape filling, we see the hydrogen end of this molecule is attracted to the oxygen end of the neighboring molecule. It's an attraction between opposite charges. It's not positive one and negative one, but it's a charge that's always there. Here we see, I think this is ethanol. So here we have an ethanol molecule, and we've got an oxygen-hydrogen bond. The molecule's polar, and we have an oxygen-hydrogen bond. There's going to be hydrogen bonding. So we'll get some attraction between the hydrogen on one molecule and the oxygen on a neighboring molecule. Any questions?
Does it matter like which hydrogen attaches to the oxygen?
It doesn't matter which hydrogen is attached to the oxygen, as long as there's a hydrogen attached to the oxygen, then you can have hydrogen bonding. But these hydrogens attached to the carbons are not the part that's going to be attracted to this oxygen. What happens here in this hydrogen-oxygen bond is it is a more polar bond, and so oxygen is pulling the electron density away from the hydrogen, and so this one becomes a little bit positive. Over here with the carbons and the hydrogens, they are so close in electronegativity that they share pretty equally. And so these aren't going to have any sort of a charge on them. Any other questions? So important to remember, hydrogen bonds are between molecules. Chemical bonds are between individual atoms within the same molecule. So hydrogen bonds are only like 2 to 5% as strong as a covalent bond. So covalent bond is much, much stronger. We can again compare some similar compounds. Here we have ethanol and dimethyl ether. We can tell that this is a polar molecule. It's got hydrogen over here on the end. This one is also going to be polar. If we look at the Lewis structure, the oxygen there is going to have two lone pairs on it. And so that causes us to say that this is a polar molecule. The ethanol is also polar. You could think of that a couple of different ways. You could say, well, this is the most central atom. There's no lone pairs on that, but the atoms bonded to it are not all the same. So they're both polar. They have identical molar masses because they have the same number of carbon and hydrogen atoms. But their boiling points are very different. Ethanol is a liquid at room temperature, boils at 78 degrees Celsius. Dimethyl ether is a gas at room temperature, boils at minus 22. Well, does dimethyl ether have an ET phone home bond in it? Does it have oxygen bonded to hydrogen? No, it doesn't. There is oxygen and there is hydrogen in the molecule, but the hydrogen is not bonded to the oxygen. You have to have fluorine, oxygen, or nitrogen bonded to a hydrogen. Here we have oxygen directly bonded to hydrogen, and so that's what we need for hydrogen bonding. So this molecule has hydrogen bonding, a lot stronger attraction between the molecules, and so to get this to boil, to go into the gas state, requires a lot more kinetic energy. And we see the same sort of difference with the melting points. Yes?
So is the structure of the atom, or the molecule, when it consists of the same atoms, does it have a lot of effect on some of its chemical properties?
Yes. So these are examples of isomers. They both have 2 carbons, 6 hydrogens, and 1 oxygen, right? But because of how the atoms are connected to each other, because of their structure, they have very, very different chemical and physical properties. Ether, this isn't the one they use as an anesthesia, but it would do the same thing. Ether, you get a good whiff of that and it'll knock you out, be unconscious. And it's a gas, right? And ethanol is what's in beer and vodka and stuff, and you drink it. And you drink enough of it, it'll knock you out, but not in the same way as ether would. Very, very different. And that's one of the really cool and vexing things about organic chemistry, is you can have exactly the same number of atoms of each element, and you can put them together in all kinds of different ways and end up with very, very different compounds. So very cool and very problematic at the same time. We don't think of water as being a very strange and extraordinary substance because we are so familiar with water. And yet when you compare water to other compounds that are similar in terms of what they're made out of, it has some very remarkable properties. In this graph, we're looking at the boiling point as a function of molar mass. So here are the group 4 elements: carbon, silicon, germanium, and tin, and they will all form compounds with hydrogens, 4 hydrogens to 1 of the group 4A elements. And so we can see there's a general trend. It's not linear, but there's a general trend that at higher molar mass, you have a higher boiling point. And we can attribute that to increased dispersion forces, right? This being a larger molecule is going to have a big floppy electron cloud that can get pushed around. And CH4 is smaller and tighter, and it isn't as easy to push around. So the dispersion force here is weak, and we see that in a lower boiling point. Okay? If we go over here to group 6A, H2S, H2SE, H2TE, we also see this trend of increasing boiling point with increasing molar mass. And the reason that the group 6A compounds are all above, higher in boiling point, is that these all have lone pairs on their central atoms. Whereas Something like silicon tetrahydride does not. So these are polar. So the group 6A molecules are polar, and these are going to be nonpolar. And so we see that this line is higher boiling points, higher melting points too. And then there's water. Now, we would expect, based on the trend from these other two, we would expect that water would be somewhere down there close to minus 100 degrees Celsius for its boiling point, right? Because H2O is smaller than H2S, and so it should have weaker dispersion forces. And yet the boiling point is super high, 100 degrees Celsius. But what does H2O have that none of the rest of these have? Hydrogen bonding, right? They all have hydrogen atoms, right? But H2O is the only one that's fluorine, oxygen, or nitrogen with hydrogen. And so the strong hydrogen bonding holds the water molecules together until they get to a much higher temperature than the other compounds. If we didn't have hydrogen bonding, all the water on our planet would be in the gas state. How would that work out with life as we know it? It would not. Oceans, gone. No ice. All of the water in your body would be a gas. It's just not going to work at all, right? Which has a higher boiling point, HF or HCl, and why? And in this chapter, we'll have a lot of questions along this line, saying, put these in order of boiling point, or put these in order of melting point, or which one is the stronger intermolecular forces, all of those sorts of things. So look at the two molecules and figure out, well, what kind of a molecule is this? What kind of forces does it have? Is HF polar? Yes. Right? It's two different nonmetals. Is HCl polar? Mm-hmm. They're both polar, therefore they both have what kind of force? Dipole-dipole forces. Do they have dispersion forces? Yeah. Everything has dispersion forces. So they both have those. I didn't plan this out very well, but that's okay. The third type of intermolecular force that we talked about was hydrogen bonding. Do either of these have hydrogen bonding? Yeah. F, O, or N bonded to hydrogen. Well, we've got the fluorine and hydrogen, so this has hydrogen bonding. The molecules stick together more strongly, and so you have to get it to a higher temperature before you can get them to separate. So HF is a higher boiling point because it has hydrogen bonding, which is a stronger intermolecular force. Any questions? The last one, which is an important force, but I would say is not an intermolecular force, is the ion-dipole force. The other forces all occur in pure compounds. This only occurs in a mixture. And this is the attraction between an ion and a polar molecule. So an ionic compound mixed with a polar compound. It is very important, especially in the formation of aqueous solutions, and it's also very strong. Here we see an illustration of this. So if we're dissolving salt in water, the salt will separate into anions and cations. The anion, chloride, will be attracted to the positive ends of the water molecules. So this is an attraction between the dipole of the water and the ion-dipole force. And the sodium ion is positive, and it will be attracted to the negative end of the water molecules, again, ion-dipole force. These forces are stronger than hydrogen bonding because one of the charges here actually has a full positive, full negative charge. The magnitude of the charge is larger, so the strength of the force is larger. Only between ionic compounds and polar compounds. So table 12.4 from your textbook summarizes all of these. And we have this general increase in strength as we go down: dispersion, dipole forces, hydrogen bonding, and ion dipole. But we do have this qualifier at the bottom. The dispersion force can become very strong, as strong or even stronger than the others for molecules of high molar mass. And so when you're comparing compounds, you want to make sure that they're not differing in a bunch of different ways. You can't compare a polar compound that's very small with a nonpolar compound that's very large and be able to make a reasonable comparison. If they're the same size, you can compare them based on polarity. If they are of the same polarity, then you could compare them based on size, but we're not going to go into trying to do both at the same time. So, which of these substances has the highest boiling point? How can we even start to figure this out? What affects the boiling point? Intermolecular forces. So we need to identify what kind of intermolecular forces do these things have. Let's start with N2. Is that a polar molecule? No. So it only has dispersion forces. The other two also have dispersion forces. Everything does. We've got carbon monoxide, and then we've got methanol. For carbon monoxide, it really doesn't matter if it's a double bond, a single bond. It just really doesn't matter because there's only the one bond. Is this bond polar? Yeah. So this is polar, so what does that mean in terms of intermolecular forces? It's got dipole-dipole forces. Is this one polar? Yeah. It's lopsided, right? Does it have dipole-dipole forces? Yes, it does. Do either of these have hydrogen bonding? Yeah, this one does, right? Here we have oxygen bonded to hydrogen. So that one has hydrogen bonding. The carbon monoxide does not. Is there a huge difference in size between these molecules? No, they're pretty close, right? It's not like you've got 15 carbons on one and one carbon on the other. And here we've got a carbon and an oxygen, carbon-oxygen, two nitrogens. Their molar masses are really similar. So who's the strongest forces? A, right? And the one with the strongest forces is going to have the highest boiling point. Because you can imagine these molecules in their Velcro suits, right? And how much Velcro there is on your suit relates to how strong your intermolecular forces is. So the guy with the hydrogen bonding, his suit is completely covered in Velcro. And N2 over here with just the dispersion forces, his suit just has little patches of Velcro around. And so you get a bunch of these people together in a crowd, and they're trying to move around. Maybe they're at a party and they're trying to get to the drinks counter or something, and they're sticking to each other, right? Because the Velcro, you can't slide past because you're sticking. And so in order to break loose and get out of that crowd, you're going to have to exert a lot of force, right? You're going to have to move quickly to jerk away. Does that make sense? So I think of at a higher temperature, that's the jerking away. You have to go to a much higher temperature before you can escape. Whereas this N2 with the dispersion force is just little patches of Velcro. This guy could probably just kind of lean away and he can get loose, right? Low temperature. I don't know if that helps or not, but there it is. I'm not going to test you on this, but I think it's important. And my computer's having an issue. Hydrogen bonding is extremely significant in your DNA. I know some of you are biology students as well, so you may be familiar with some of this. Your DNA is composed of a backbone of phosphate and sugar molecules strung together, and then each of these sugars has a base on it, and these are the bases: adenine and thymine, cytosine, and guanine. So these are attached to those sugars, and this would represent one strand of DNA, which I guess you could call RNA. In the DNA, you've got two strands together, and they're held together by hydrogen bonding between the base units. Thymine and adenine both have two places that they can engage in hydrogen bonding. We've got oxygen, nitrogen here. I'm sorry, hydrogen, nitrogen. You get the idea. Those things there. And guanine and cytosine, they can make 3 hydrogen bonds. And so cytosine and guanine will hook together very nicely. Adenine and thymine hook together very nicely, clicking together almost like magnets. And so your body can replicate the DNA by separating the two strands and bringing in new base units that correspond to the ones that are existing, and then hooking them together with that sugar phosphate backbone. And you can duplicate the DNA. It's very, very cool. Anybody have any questions about that? So it's kind of like your DNA is held together by magnets called hydrogen bonds.